In this part of the video, I'm going to explain why a histogram is useful. I'm going to explain the purpose of a histogram. But first, I want to go back and talk a little bit more about the idea of class width. I want to talk about how a person chooses a class width. And when you choose your class width, it's important to choose a nice number. A nice number is something like 5, 10, or 20. A multiple of 5 or a multiple of 10 will give you a nice number. You don't want to choose an unusual number like 7 because then your intervals would be something like 1 to 7, 8 to 15, 16 to 21, and you don't want that because that would look a little bit unusual. It would look much nicer to have intervals like 0 to 9, 10 to 19, 20 to 29, because those are categories that people are more familiar with. They just look nicer to most people. So you want your class width to be a nice number, and also you want to choose a class width that gives you the right appropriate number of bars. And there's actually a formula that'll tell you what your class width should be so that you have the right number of bars in your histogram. And I'm not going to go into that formula in this video, but I want you to know that that formula exists, and I might share it with you at some point if I ask you to create a histogram, maybe. But really, at this point, I just want you to understand that there are guidelines for choosing a class width for a histogram or for a table. So now let's move ahead and talk about the purpose of a histogram. The purpose of a histogram is to show the shape of a data set. Whenever you record a set of quantitative data, like heights, ages, or incomes, the data values that you've gathered are going to have a shape. So if you've recorded 100 ages, those 100 ages will have a shape. If you record 100 heights, those 100 heights will have a shape. And if you record 100 incomes, those 100 incomes will have a shape. And when you make a histogram, you can actually see the shape of your data. And a data set can have a variety of different shapes. There's different shapes that could appear. And one type of shape that a lot of people know about is called a normal distribution or a bell-shaped curve. Normal distribution and bell-shaped curve have the same meaning, but in everyday life, people use the word bell-shaped curve more often. And the term normal distribution is used more often in statistics classes or in the field of statistics because it's the more technical word. So I did my best to draw a picture of a normal distribution or bell-shaped curve. It's not perfect, but I think it's pretty close. And if you drew a line to outline the tops of the bars, it would look like a bell or pretty close to a bell, and that's where the word bell-shaped comes from. It's called a bell-shaped curve because if you draw a line to outline the top of the histogram, it looks like a bell. And you might be wondering where the word normal comes from. I'm not exactly sure where it comes from, but I think it might be called normal because a normal distribution is a shape that appears in a lot of situations in everyday life. So that might be why it's called normal, because it's not unusual. But I'm actually not totally sure where the word normal comes from. In statistics, it's common for people to take a term or a word from everyday life and give it a new meaning. So this is one example of that. So the word normal is a word from everyday life, and people in statistics have taken that word and given it a new meaning, which is a bell-shaped curve. And the meaning of a word, well, if a word in statistics is also used in everyday life, then the meaning of the word in statistics isn't necessarily the same as the everyday life meaning. So the word normal in statistics doesn't have the exact same meaning that the word normal does in everyday life. So this is something that you just need to be aware of going forward. If you see a word in our class and you recognize that word from everyday life, don't automatically think that it has the same meaning that it does in everyday life. So before we move on, I wanted to say that there are a lot of things in everyday life that follow a normal distribution, or at least close to a normal distribution. One example is height. If you looked at the heights of people in the general population, the heights would follow a normal distribution, or at least pretty close to it, because in the general population, you have a few really short people, you have a few really tall people, but most people are in the middle somewhere. Also, IQs have a normal distribution in the general population because you have a few people at the low end, you have a few people at the high end, but most people are in the middle area right here. Also, personality traits like extroversion or how outgoing a person is have a normal distribution or at least close to it. Because whenever you look at a certain trait, you have some people who are very low on the trait, some people who are very high on the trait, but most people are somewhere in the middle. So really, whenever something follows a normal distribution, all it means is that there are fewer people down toward the low end, fewer people up toward the high end, and most people are in the medium or middle area. That's what a normal distribution is. So if you're ever in a class and your professor says that the exam scores have had a normal distribution, what the teacher is telling you is that a few people did really poorly, a few people did really well, but most people were in the middle area. That's normal distribution. So now let's move ahead and talk about the two features of a data set shape that can be seen in a histogram. The first one is skewness. So skewness is the amount of asymmetry or the lack of symmetry in a data set. If a data set is symmetrical, then it has no skewness. And if it's not symmetrical, if it's asymmetrical, then it does have a skewness. And the skewness is really just the amount of the lack of symmetry. So if a data set is really highly non-symmetrical, it will have a high skewness. So this first histogram right here has no skewness because it's symmetrical. Um, it's symmetrical, so if something is symmetrical, what it means is if you fold it over, it'll fold over nicely and the two sides will meet up with each other. So a face is symmetrical because if you took a face and somehow folded it over, the two sides would meet up. So if something is symmetrical, it means that one side is the opposite of the other, and the two sides are mirror images of each other. So if you look at this first graph, which is flat, and imagine that it's made out of paper, and you folded it over. You folded over the left half. I'm sorry. You folded the so that the right half would meet up with the left half. It would fold over really nicely, um, just like a card would fold over or a birthday card. So this is symmetrical and it has no skewness. This second histogram is also symmetrical, which means no skewness. If this was a card made out of paper and you folded it over, it would fold over nicely because this small bar would meet up with this small bar and it would fold over. This third one is skewed. It does have a skewness because it's not symmetrical. So not symmetrical means skewed. If this was a card and you folded it over, the two sides would not meet up with each other. So it's not symmetrical and it is skewed. So skewness is lack of symmetry. The second feature of the data set shape that can be seen in a histogram is kurtosis. And kurtosis is the sharpness or peakedness of the data. So if a data set is flat or relatively flat, it has a low kurtosis. And if a data set is peaked and it has a tall and narrow peak that really stands out, it has a high kurtosis. So what I did here was I ordered these histograms from the lowest kurtosis up to the highest kurtosis. This first one has the lowest possible kurtosis because it's completely flat. This one is a little bit sharper, so it has a higher kurtosis. And this one is even sharper, so it has a even higher kurtosis. So when you think of kurtosis, it might help to imagine this analogy. So imagine you take a histogram that's flat and you put it into a pencil sharpener and you make it sharper. If you did that, you would be increasing the kurtosis because you would be making the histogram sharper. Now, you obviously can't put a histogram into a pencil sharpener, but that's just something that you can picture if that helps you. So now I want to wrap up the topic of skewness and kurtosis by just covering a few bullet points about skewness and a few bullet points about kurtosis. So let's start with skewness. First of all, a normal distribution or bell-shaped curve has no skewness at all because it's symmetrical, right? If you made a card shaped like a normal distribution and you folded it over, it would fold over nicely. And since it's symmetrical, it has no skewness. Also, there are two types of skewness because the skewness can go in one direction or the other. If a data set if a data set peaks at the left end and it trails off toward the right, it has a positive skewness. And if it peaks at the right and trails off toward the left, it has a negative skewness. So when a data set has a positive skewness, it means that the bars are trailing off toward the positive end, toward the right. And if it has a negative skewness, it means that the bars are trailing off in the negative direction, toward the left. So you have to remember that the name isn't telling you the side that it peaks on, it's telling you the side that the bars trail off toward. So if it trails off toward the right, positive. If it trails off toward the left, negative. And it's very easy to get these switched around. But just keep in mind what I just told you to try to keep them straight. And I also wanted to give an everyday life example of a positive skewness and a negative skewness, or at least one everyday life example. So I think a good example is an exam, or when a class of students takes an exam. If a classroom of students takes a difficult exam, and a lot of people end up at the left end, not doing well, then the scores will have a positive skewness because most people are down at the low end and the bars are piling up. The people are piling up down there. If a class takes an easy exam and a lot of people do well and a lot of people pile up at the high end, then the scores will have a negative skewness. So positive skewness, think of a hard test. Negative skewness, think of an easy test. So with a positive skewness, you have a lot of D's and F's, some C's, but very few B's and A's. When you have a negative skewness, you have lots of A's and B's, these tall bars, and you have some C's and very few D's or F's because the test is easy. Also, I wanted to share an example involving incomes. So my first job when I was at high school was at Burger King, and I was making, I think, $6 an hour when I started. And if you look at the hourly wages of people at a fast food company like Burger King, you'll have a lot of people down at the low end of the population because you'll have a lot of cashiers making the lowest possible salary, and they'll all pile up at the low end of income. But then you might have some managers who are making a little bit more in here, and then you might have some regional managers making even more, but there aren't as many of them, right? There's a lot more cashiers down here than regional managers up here. And at the very end, at the right, you'll have the CEO who makes a lot of money, but they're a very short bar. They're only one person. And if you looked at the incomes of, let's say, a hospital, the incomes there might have a negative skewness because you'll have a lot of surgeons and doctors making a very high income. And so you'll have a lot of people at the high end of income, at the right end. But then you might have some support staff, maybe some people who are supporting the hospital who are making less money, but like receptionists or other support staff, but there aren't as many of them. So in a hospital, you'll probably have a lot of people piling up at the high end of income and some people at the low end, but not as many of them because most people in that population are up at the high end of income. So that's just some examples from everyday life. So basically, when you have a positive skewness, people are leaning toward the left, and with a negative skewness, people are leaning toward the right. So there are two types of skewness. Also, point number 3 about skewness is the type of skewness in the data determines whether the mean is below or above the median, with some exceptions. So if the data set has a positive skewness, the mean will be above the median. And if the data set has a negative skewness, the mean will be below the median. And if there's no skewness, like a normal distribution, the mean and median will be the same number. So whenever the data set has a skewness, the mean is pulled out toward the tail. So here it's pulled out toward this tail. Here it's pulled out toward this tail. So whenever a data set has a skewness, the mean becomes a little bit less accurate because it's pulled in the direction of the tail. It's pulled out toward the extremes. Point number 4, a value can be used to measure skewness. So far we've been talking about looking at a graph to judge the skewness of a data set, to decide what type of skewness it has. But you can actually calculate a value that tells you the type of skewness in a data set, and it's called a Skewness Statistic. And we're not going to be calculating it in this class because it's too hard to calculate, but I just want you to know that it exists. And I want you to also know how it's interpreted, how people make sense of it. So if the skewness value comes out to 0, the data has no skewness. It's symmetrical. And the further the value is above 0, the more dramatic of a positive skewness you have. And the further it is below 0, the more dramatic of a negative skewness you have. And one guideline people follow is having -2 and +2 as cutoff points for a considerable or dramatic negative skewness and a considerable or dramatic positive skewness. So if the skewness comes out somewhere between -2 and +2, it's pretty close to symmetrical. It's pretty much no skewness. And now let's cover a few points about kurtosis. So first of all, there are 3 levels of kurtosis that people talk about. So if the data set is flatter than the normal distribution, in other words, if the data has a wider and shorter peak than a normal distribution, it's called a negative kurtosis. If the data is sharper than a normal distribution, it's called a positive kurtosis. So if the data has a taller and narrower peak than a normal distribution, it's called the positive kurtosis. So the normal distribution is the dividing point between negative and positive kurtosis. Think of the normal distribution as a baseline or a starting point. If you go flatter than a normal distribution, you get a negative kurtosis. And if you go sharper, you get a positive kurtosis. And when you think of a negative kurtosis, I would imagine a bundt cake. That's kind of a good way of picturing a negative kurtosis. And when you think of a positive kurtosis, well, I can't really think of anything from everyday life that really has a positive kurtosis. But when I was in school, my teacher mentioned this old movie called Coneheads, which is based on a Saturday Night Live skit, and they have these really tall and narrow heads. And he said that is like a positive kurtosis. And actually, before we move on, I wanted to share a few everyday life examples, or at least one everyday life example of these types of shapes. So if you, and I'm not completely sure about these, but these are just my best guess. So if you looked at the ages in a city or a really big population like a city or a county, the ages would probably have a negative kurtosis because there wouldn't be one part that really stands out, because each age group would appear roughly the same number of times. So you would probably in a city or a county, you would have some people in their teens, some in their 20s, some in their 30s, some in their 40s, and each of those would probably have about the same frequency. They would all probably be about the same number, so it would be fairly flat. So it's not likely that there would be one age group that would be hogging a large number of people. It would probably be pretty evenly spread out. An example of a positive kurtosis, or at least I think, would be hours of sleep. Because if you looked at the hours of sleep in a big population, you would probably see that a lot of people fall somewhere between, let's say, 5 and 8 hours of sleep, or maybe 5 and 7. And those bars would be very tall. And you'd have a lot of people in that narrow area between 5 and 7. But then you would have very few people below 5 and very few people above 7. So it would be kind of like it falls sort of off a cliff when you go below 5, and kind of off a cliff when you go above 7. At least that's what I'm thinking it would probably be like. I might be wrong. Um, but that's just one possible example of a positive kurtosis. So whenever a data set has a positive kurtosis, it means that there's a lot of people in this narrow area and very few people outside of that area, which is why the histogram ends up with this really tall, narrow peak. And a negative kurtosis means that people are kind of more evenly spread out across the range of possibilities. Now I just want to give a summary of histogram shapes. First of all, I wanted to mention that there's also a statistic that can be used to measure kurtosis. And a normal distribution has a kurtosis of 0. And if the kurtosis statistic comes out below 0, you have a negative kurtosis, meaning flatter than a normal distribution. And if the kurtosis comes out to a positive number, you have a positive kurtosis, meaning sharper than a normal distribution. So that bundt cake that I showed you is somewhere down at the negative end. The normal distribution is at 0, and the sharp graph I showed you is somewhere up at the right end. And we're not going to calculate kurtosis by hand either because it's also too complicated. And to wrap things up, here's a summary of histogram shapes. So here we have a normal distribution with no skewness. We have a negative skewness here and a positive skewness here. I drew the normal distribution just as a reference point for you to compare this to. And down here, we have a normal distribution. And here we have a negative kurtosis, which is flatter, and a positive kurtosis, which is sharper. And that's it for this topic. In the next topic, or the topic after that, we'll continue to use the idea of a normal distribution.